All right, hello everyone. We have our seminar today, which will be given by Anna Zamojska-Dzienio. She's my longstanding colleague from Warsaw University of Technology. I've been there a few times. Always felt myself almost at home in that city, like with a lot of kind friends and bright mathematicians, as usually in Poland. And I'm very glad that Anna got a position on a Fulbright scholarship for this year as a Fulbright scholar at Iowa State University. And we even hope to get her in New York State area sometime, like in a month. So she will come in person as well. So, but today she will be giving a virtual talk at our seminar. And this is about the construction of multi-permutation solutions of the Yang-Baxter equation of level 2. Please.
Thank you very much for invitation and introduction. And these are results of our joint work with Premysl, Jedlicka and Agata Pilitowska. And I start with introduction you to the topic of Yang-Baxter equation. So general situation is that we have vector space and a solution of the Yang-Baxter equation will be just linear mapping defined which satisfies the following condition. And the aim is to find new classes or classes of solutions of such equation. And equation is important in physics. And so some simplifications were introduced to the topic by Drinfeld. He proposed to consider set-theoretical solutions. And the idea is that instead of taking vector space, whole vector space, one can just consider a set X, which is a basis of this space. And then consider two mappings going from x squared to x, sigma and tau, which satisfy the following condition that this mapping now can be extended to the original solution of the Yang-Baxter equation. And so it is quite natural simplification. And during my talk, I am working only with set-theoretical solutions. So even if I forgot to add this adjective, I am thinking only about set-theoretical solutions. And okay, this condition on mappings sigma and tau says that in fact this R mapping we had in the original for vector spaces. So R now is just have two coordinates sigma and tau. It satisfies the braid relation. And this braid relation, so for this set X, is defined as follows. And I mean by, so applying, for example, identity times R to the triple, now it is applied to the triple, that what I obtained is, so identity for first coordinate mean I have X here, and then I apply R to the second and third coordinate. So finally, I obtain something like that. And then, of course, again, I have a triple. So I apply R times identity, meaning I apply R to the first and second coordinate now, and identity to the last coordinate, and so on. Of course, I do it on the left-hand side, on the right-hand side, and then in fact, as you will see in a minute, I will obtain some special conditions, yes, on these operations sigma and tau. So some important classes of solutions, set-theoretical solutions. So people were mainly studying non-degenerate solutions, meaning that this mapping, sigma and tau, when we establish the first coordinate in case of sigma and the second coordinate in case of tau, so they are bijections. Yes, with such setting, then they are just mappings going from x to x, yes. And they are bijections, so then we say that this solution is non-degenerate. And we say that it is involutive if R squared, so R composition R with itself is just identity on x squared. And we say that it is square free if the following condition holds. And in this talk, we will consider, so first set-theoretical, then all conditions, so non-degenerate and involutive solutions. So it is our aim of study. And okay, in fact, square free, we will see just once during this talk. And why people are interested in these involutive solutions? Because then, in fact, the operation tau can be expressed, so it's uniquely determined, in fact, by the operation sigma. So it is enough to consider one operation instead of two, because then the second one is just determined by the first one. And it was already noticed by Wolfgang Rump in his paper, you can see here. So our approach uses Weirachts, some algebras which are important in low dimensional topology. They were introduced by Fenn and his co-authors in this paper, and already they noticed that there is one-to-one correspondence between non-degenerate solutions of the Yang-Baxter equation and Weirachts, and this correspondence is given by the following fact. So considering our mapping R applied to X and Y, okay, it means that we have this sigma and tau in our situation. Then, okay, sigma was just mapping going from x squared to x. So it is just binary operation. So let's denote it by circle, white circle. And here, okay, the second operation also is just binary operation. So let's denote it by black circle. And usually if one works with such algebras called magmas, yes, one calls this properties, property. It is, shortcut for it, it's written it's like that, meaning that it is what is called left translation by X, and here we will have right translation by Y. And okay, it is similar case, for example, for Cayley theorem for groups. Yes, so it is exactly the same notation. It works for magma. And but the reason why they introduced these algebras was different than just Yang-Baxter equation. But already in their introduction, they noticed this connection. In introduction to the paper, but somehow it was in fact not used. So this approach was not used, in fact, until 2015 to some papers written by Patrick Dornoux. I will mention it. So perhaps just a few words about Weirachts. Yes. So similarly as quandles and racks, which were introduced independently by Joyce and Matveyev, are algebras which are connected with classical knot theory. So quandles just reflect this first, second, and third Reidemeister move, and racks only second and third. So similarly, biracks and biquandles were introduced by Penn and his co-authors as representing virtual knot theory. Virtual knot theory was introduced by Kaufman. There are two types of intersections in this diagram of knot, and it is, I would say, the normal one and virtual one, yes. And this is the reason why they needed more operation than just in quandles. And okay, what is the connection? So names are similar. What is the connection? Yes, and both algebras, as all algebras are applied in this knot theory. And so, what is this connection? So, assume that we have a birack, and assume that this operation is just projection on the second coordinate. Yes, so as we could see here. Then it forces that this the set X together with these two operation must be a rack. And similarly, okay, if one assumes that this operation is just projection on the first coordinate, then it forces that this must be rack too. So it is this connection by rack. So it is not the case that, okay, it means that we have structure of racks on both, so in both cases, yes, this connection. Okay, so equational characterization of biracks was given by Dawid Stanowski, and it looks as follows, yes, as you could see. So these two lines are conditions which says that X together with this first and second operation is something which is called left quasi-groups, and the X together with the third and fourth operation is something which is called right quasi-group. And now these conditions, these are these conditions we just obtained for this braid relation, and I introduced to you. Okay, just rewrite in the language of dots, yes, instead of sigma and tau. So it is these three, okay, perhaps not very nice looking identities, but they come just from this braid relation. And this is just equational characterization of biracks. And birack is involutive, so this condition that R square is identity on X square translates then this way. So we obtain such identities. And remembering that we had this structure of left quasi-groups with respect to this operation and right quasi-groups with respect to black dot operation, meaning we have division, but here from left-hand side, here from right-hand side. It gives us this observation that in involutive biracks or in involutive solutions, one has that, okay, one operation, so say black dot can be, is determined, yes, can be expressed with use of this first and second operation. And similarly, okay, if you prefer to focus on black dot operation, that the first operation can be just determined by this then third and fourth operation. So it is what we obtain, and it is just translated to the language of biracks. we are working here with Biracs in our approach because it is very convenient for us. I would say our roots come from universal algebra, so working with just algebraic structures is very convenient for us and gave us some new results in this topic. Rump in his paper also showed another approach. He didn't use Biracs, and he showed that involutive solutions of the Yang-Baxter equation can be expressed in one-to-one correspondence with non-degenerate cycle sets. He introduced such kind of algebras. So cycle set is a left quasi-group which satisfies additional condition. It looks like that. So if you just have a look into it, it means that, we can here change the order of the variables, but then here we have to take this variable. It is how it looks like. And non-degenerate here means that the demapping defined this way is a bijection. And Rump used this approach via non-degenerate cycle sets. So, of course, as you remember, involutive solutions, non-degenerate, involutive, set-theoretical, all these adjectives we have here, and are in one-to-one correspondence with these non-degenerate cycle sets. On the other hand, they are in one-to-one correspondence with involutive Biracs. So what is connection between non-degenerate cycle sets and involutive Biracs? So if we take Birac, which is involutive, then in fact, what we obtain here will be exactly non-degenerate cycle set. One important thing is that, the order of operation changes. So it is in fact still left quasi-group, what we have here, but means that this cycle condition we have there is just for this left division, yes, in this Birac. And it changes a lot. I could see some preprints in archive where authors didn't notice that it is a change of order and the results were wrong. And here is this paper by Dornois, which I promised. And he noticed this connection and recalled this connection, first noticed by Fenn and then somehow forgot and not used, about Biracs. As I said, Rump didn't use this language of Biracs, but theorem, because here we can see, we have Birac means we have a structure of non-degenerate cycle set here, but the other way around, yes, starting from this non-degenerate cycle set, how to get the involutive Birac. So it is the way we do it. So we take in our Birac. So the first operation in our Birac will be the second in this non-degenerate cycle set. Then, we have this operation. So this left division here will be this one. And how to obtain this dot operation, you remember it is determined by this first two. So it will be obtained this way. And here is why this non-degeneracy of this operation T was necessary, was to define this, in fact, this right division. Yes, so because definition says that it will be just some unique element due to this bijection, yes, which satisfies the following condition. So important is that, yes, we have this one-to-one correspondence between two approaches. Doesn't matter whether we prefer to work with non-degenerate cycle sets or with involutive Biracs. And so going to these multi-permutation solutions, I must recall some relation introduced by Ettinghoff and his co-authors in fact, the first paper, I mean the first, I would say, important and not noticeable paper connected with this quantum Yang-Baxter equation. And so it is from 1999, so no language of Biracs yet. Yes, Biracs were not introduced yet. And so they introduced the equivalence relation for involutive. They were working only with involutive Biracs here. So involutive solutions, yes. And they introduced the following relation, equivalence relation. So two elements of set X are in this relation exactly if the tau operation, so this where, okay, we have fixed the second coordinate. So in first case, it's X, here Y. So now we have mappings going from X to X. So if they are equal, these mappings. Okay, equivalently, if one prefers this operation sigma, we can define it using operation sigma. And they showed that the quotient set then, via this equivalence relation, again can be endowed with a structure of a solution, and they called such solution the retraction of the solution. And they introduced also the notion of multi-permutation solution of level K, because of course then we can repeat this, iterate this procedure, yes, because taking one retraction, we have solutions, so we can take one more time retraction and so on. And the smallest K where it stops and gives us something which is called trivial solution, so just one element solution, is, so this K, for this K, we say that this solution is multi-permutation solution of level K. Of course, there exists so-called irretractable solutions. So it can happen even in finite case that this, I mean that we never obtain this one element set, that it stops at some moment and we don't get anything new. And this is what they introduced. And so this gives new classes of solutions with, as you could see, nice description here. So we focused on multi-permutation solutions of level 2. So we have these involutive multi-permutation solutions of level 2, and also such solutions were studied by Tatiana Gateva-Ivanova and Cameron, and they noticed already that multi-permutation solution of level 2 means that in the corresponding Birac, okay, they also didn't use this Birac's approach, but we just, so it is our interpretation, but this, that it must satisfy the following condition, this is what they called two-permutational, this is this condition, yes. So we have, again, additional identity, in fact, for these involutive Biracs to give us multi-permutation solutions of level 2. So as you could see, we can exchange the most inner exchange. I mean, it doesn't matter what is the most inner variable here. And each two-permutational involutive Dirac, in fact, originates from involutive two-reductive Dirac. So we have this kind of equation here. So and in fact, this kind of identities were studied in this magma settings, so just algebras with one binary operation. And many results were obtained also in case of quasi groups, yes, with these conditions. And the relation between two-reductivity and two-permutationality is that, okay, each two-reductive magma will be two-permutational, but not every two-permutational will be two-reductive. So there exist two-permutational which are not two-reductive. In case of this, okay, this is this moment when square-free solutions, so this one where R of XX is just again XX. And in this case, they are the same notion. Yes, so then two-reductive and two-permutational means exactly the same for square-free solutions, but only that. So now we will, so knowing that in fact these two-permutational involutive Diracs are, now I said that only in some way given by these two-reductive Diracs, we want to have closer look to these involutive two-reductive Diracs. So how they can be obtained? Yes, this two-permutational from two-reductive. And so each two-permutational involutive Dirac, okay, we called this operation different symbols. So we know that there exists a two-reductive involutive one and some bijection of the set X such that this first operation star here is given by first operation in this two-reductive involutive one, but together, so Y is transformed via this bijection. So it is the condition, so how it is the way how we obtain from two-reductive involutive one just two-permutational involutive. And okay, in case of involutivity, in fact, knowing the first operation, we know all others. Yes, so it is just enough to have this prescription for this first operation. So, how can we obtain then these two-reductive involutive ones? So, our construction is based on abelian groups, and is, as you could see, very simple. So it is, so then set X is just a disjoint union of abelian groups. These abelian groups are generated by some elements which will play the role of some distinguished constants here. And what we obtain, so how to define operation of this disjoint union of these abelian groups. So they are defined this way. Yes, so in fact, okay, it is enough to define this one, but okay, you can see how all other then must look like. So it is just, so if we want to have this first operation, it is just enough to add to Y. So addition is just taken from this abelian group to add this distinguished constant. So to have this left division, it is enough to subtract distinguished constant. And okay, for this third operation, it is defined this way. And the last one, so this right division, we have such construction. And this way we obtain all involutive to reductive Biracs. And having such representation, we will have also easily we get isomorphism theorem, but first, okay, I would like to say a few words about two reductive Racs. Because if you look at this theorem, and in fact, it gives us also the structure theorem for how to obtain just two reductive Rac. So two reductive Rac will be okay, we obtain, so means it is this part, and then it means that just, okay, exactly the same construction, just forget about this part. So this way we obtain also construction for all two reductive Racs. And as I mentioned, okay, then due to this representation, we obtain isomorphism theorem easily. So, so when two involutive Biracs are isomorphic, so in fact, okay, we can represent them as the sequences of groups, yes, together with these distinguished constants. And in fact, it means that, so it is taken over some set I, so which is the set of indices for these groups. And it means that this group must be in sequences, must be isomorphic. So there exists group isomorphism between this group in first and second sequence for first and second Birac, involutive Birac. And okay, it is only due to permutation of, in fact, of these indices, yes. And also, okay, this isomorphism, so this distinguished constant should behave well. So it is how they behave, yes. So distinguished constant taken from this sequence of A groups must agree with the sequence of distinguished constants for the second sequence or the second involutive Birac. So returning to solutions. So solution, so name distributive solution is used in such case. So one says that a solution, so solution is distributive if it's Yang-Baxter group. So it is just the group generated by this sigma X mappings, or in fact here, if one prefers tau Y mappings, it is also good. Groups will be just isomorphic. So it is this, they will be equal in fact. And so we have this Yang-Baxter group. So the Yang-Baxter group is just a subgroup of automorphism group for this solution. So we just take automorphism of solutions, remembering that they should work together with this sigma and tau operations. So such solution is called distributive. So what we can say about these solutions, involutive solutions of multipermutation level 2? It turns out that in fact there are just two classes, two disjoint classes of such solutions, distributive ones, so those one where the Yang-Baxter group is the subgroup of an automorphism group, and those one which are not in this class, so non-distributive. And what is perhaps, okay, before this theorem. So in fact, distributive ones are exactly, so they are in this correspondence with involutive biracs, which are two reductive. And non-distributive ones are in correspondence with these involutive biracs, which are two permutational, but not two reductive. It is, I mean, this division of these two, how it divides for these two disjoint classes. Among the others, yes, it is quite easy to recognize distributive solutions because, okay, assuming that we are given such solution, yes, of level 2, so it means that exactly that, in fact, all tau x must be just inverse, so each tau x is just inverse mapping to sigma x. It is how it works. Quite easy to recognize. So now we go to the construction. So how to construct all solutions of multipermutation level 2 of size n. So we start with distributive solutions here. So as you remember, they correspond to these two reductive involutive biracs. So for all partitionings like that, we just take abelian groups of these sizes, yes, in this sequence. We just distinguish some constants, and so using these constants to generate these groups, we can construct solution on this disjoint set of disjoint union of the supports of these abelian groups. And okay, the theorem was telling us about this, so it was in this language of biracs. So operation, so in case of solutions, it is just, you know, rewriting it for the language of sigma and tau, yes. So as you remember, it was this x white circle y, and it is, so I should add to y this distinguished constant. And okay, for tau, it was this x black dot y. I should subtract from x this distinguished constant. So it is how we construct these solutions. And now, okay, we use, of course, isomorphism theorem just to have them up to isomorphism, yes? So then we will enumerate them finally. So here we have this isomorphism theorem, which allows us to consider them only up to isomorphism. Okay, so as you remember, distributive solutions gives us non-distributive ones, meaning recalling it again in language of involutive biracs. So each two permutational one comes from some two reductive one. So here, okay, we just take our found already distributive solutions, but the procedure, okay, we use this theorem which says that, okay, we have to just use then some special bijection on set X, yes. And of course, we have some just technical properties, technical conditions taken on this bijection here, just to work well and just to obtain not all two permutational solutions, because some of them we have already, yes, with this two reductive, but only non-distributive, meaning we want to have only two permutational which are non-two reductive. So these are these, as I said, just technical condition, and finally having them, we obtain these two permutational solutions which are not two reductive. The problem is that we don't have isomorphism theorem here. So, and we know, we have examples that it can happen with this procedure, that having two reductive solutions, so having two different distributive solutions, we can obtain the same non-distributive solution. Okay, with different bijections, but we can obtain the same object. But nevertheless, we could use it somehow to this enumeration. And I will start with enumeration of racks of small order. So with our construction, we were able to enumerate all two reductive racks of size n up to isomorphism. And we were able to do it till n equal to 14. And our results were then useful, applied by Wojciechowski and Yang. There's the paper where they published it, and you can also see this sequence. And they used it to enumerate racks. And in fact, previously, only the number of racks till the 8, size of n, 8 was known. And Wojciechowski and Yang approach was that, okay, notice that, okay, there are a lot of two reductive racks. Yes, as you could see, a lot of them. So their idea was, okay, roughly speaking, yes, but okay, so it means that we don't have to focus on two reductive. It was already counted by us, but focus on non-two reductive and try to calculate them. And similarly, because of course they could also excluded some other classes, so then more or less they, for this, what was remaining, they could use just brute force method, yes. And it improved this enumeration of just racks just to 13, yes. Okay, for 14, it is not, no. There were too many of them. But as you could see, numbers are really, the one can say the most, we'll see it later, is this conclusion that most, at least for small order, most racks are two reductive. There are nice explanation of these facts using universal algebra tools, yes. They are subdirectly irreducible, yes, but it is not the topic of today's lecture.
I have a question about the previous one. So, yes, the number of racks is 9 and 10 is 15 by 26, but this is actually recently new, right? Or is it old? The 9, yes.
I think it was still. I think it was till 8 previously. I mean, before Wojciechowski and Yang did it.
Okay, that means you have to update the online integer sequences because they only know until 8.
No, I think I checked this today, is preparing, and just Googling, yes, I found it. But okay, so perhaps I will discuss it with, I think, with Peter, yes, of course. Thank you. I mean, I found some sequence. I was happy, yes, our name was also there, yes. But okay, perhaps I should have, a closer look, in fact. Yes, thank you. And okay, returning to solutions, yes, it was, so I would say that these two reductive racks were, for us, there were some side effect, yes, of our investigations. involutive solutions, so the number, okay, number 8 where it is stopped. So it was known, the number until 8 was known, and it was already due to Ettinghoff and his co-authors in this paper from 1999. Yes, they found the number of all involutive solutions. Of course, with all these adjectives I am not saying now. Set-theoretical, non-degenerate, what else? I already saw involutive. I think all adjectives I said, yes. And also, so it was the results. So as I said, what we were able to do, we were able to find these distributive ones, the number of 4 distributive ones. Okay, in fact, if it is, so why we stopped at 8? Because of this brute force needed for non-distributive ones, yes. And it is the reason, because as you remember, so this is exactly the number of 2 reductive racks. So in fact, 2 reductive racks or just distributive solutions, we have up to 14, yes, already. But because we have to work with non-distributive, finally, I mean, to decide which are isomorphic with just using brute force, okay, we were not able to go farther than till 8. But so as you could see, so multi-permutation solutions, involutive solutions of level 2 are, so we have these numbers. It is just sum of distributive and non-distributive. As you remember, yes, we have these 2 disjoint classes. And again, one can see that this is okay, most, at least at this small order, most of multi-permutation solutions are distributive, and okay, it is, one can't say that okay, most of involutive solutions are multi-permutation of level 2. Yes, it is, but okay, many, as you could see, many of them important, really important. So some conclusions about these numbers, yes, which, okay, can be also noticed from these tables I presented. So already Blackburn had noticed that this least upper bound for the lower upper bound for 2 reductive racks is like that. We were able to show that, in fact, it is also upper bound for 2 reductive size, up to, of course, isomorphism. So conjecture is, but it is just conjecture, which we could so observe, yes, for these 2 reductive racks, that probably, so this is just the number for all racks. So in other words, saying the same, that it is not only for the small orders, yes, that 2 reductive racks are, I mean, the dominating class, yes, for racks. And going to solutions. So again, we were able to show also this upper bound for these multi-permutation solutions of level 2. And okay, as you could see again from these tables, they are not here, not dominating class, but okay, it is enough of them, okay, that as we could see, to have this conjecture that about the number of all solutions. Yeah. And so final question, still open question, is how to proceed with higher levels. Yes, we have, as you could see, these multi-permutation solutions for level 2. So what about level 3 and further? Yes, unfortunately, this construction couldn't be easily generalized because there is, I mean, between many, hidden technical details, it is that these two reductive racks or two permutational racks. So in fact, okay, two reductive racks are medial. Yes, it is some special property. But it allowed us to use some other results connected with enumeration of medial quandles. So what I have presented here mainly is based on this paper. So if you are interested in any details, yes, so please have a look there, or of course you can ask questions. Also, some properties of this retraction relation, and in fact, our first paper where we started this approach via biracks, and it was successful. So this is the approach we use now. So it is the first paper where we started it. And as I said, we were using here the fact that these two reductive racks, okay, they are not idempotent, so they are not quandles, but they have this property of mediality. And we were able to adapt some construction, okay, in some way, the construction we had before in this paper, also joined with David Stanowski. So thank you for your attention.
Thank you very much. Very interesting talk. That was very long in the sense like was algebraic, right? And then
yes,
turned into combinatorial one.
Yes.
But it started as a physics. So like I really like how many turns happen here.
But you can see here how algebra is really useful, because these previous numbers were just found, I mean, up to 8, just with brute force. And it couldn't go further. So with these structure theorems, and which is purely algebraic, and I mean study of purely algebraic conditions, yes, allowed to obtain representation theorem, isomorphism theorem, and so on. Yeah.
Yeah, and we were lucky that distributive really take a big portion of it, right? So where you handle a lot. So in this regard, I have a question. So for this non-distributive solutions, you're saying that each of them coming from distributive one, right? But then because they could become isomorphic, then why it's you have a little, there are really few, right, compared to distributive ones. Does it mean that for every non-distributive, you could kind of consider maybe partition of distributive ones that might bring to the same solution, and so, or it's not structured that way?
No, it is not. Unfortunately, it is not like that. Yes, we really hoped, yes, that it will be something. Unfortunately, non-distributive ones behave badly. Yes.
So it means that you cannot look into a portion of distributive ones that bring to the non-distributive isomorphic.
No.
No. All right, other questions?
I have one. So what I understand is the quasi-groups that you mentioned are infinite, right? Or can be finite? The quasi-groups that you mentioned in the whole talk.
So they can be infinite, we don't have, I mean, this, of course, they can be infinite. Okay, when we talk about enumeration, of course, it is about finite, but I mean, this theorem was absolutely general. I mean, the theorem, for example, how to obtain two reductive rank. It really don't depend on being finite or infinite. So you have
or infinite quasi groups. So how you do experimentation in this? It looks very complicated to do experimentation, right? So do you use any software or something to do experimentation?
As for this, okay, even to get some examples, yes, I mean,
exactly.
Of course, yes. Okay, it was Premysl Jedlicka role, yes, here. And yes, he was using maze, I think, yes, it is called this, and
I'm not familiar.
And I think, yes, it is some, yeah, I mean, yes, he was using software. Yes, okay. I don't want to guess, name.
Yeah.
Okay. There are also, GAP, this GAP, G-A-P.
Yeah, I know GAP.
Yes. So definitely, I mean, Premysl is,
but GAP is just
about
up because GAP is for groups, but not for quasi groups.
Yes, but I mean the main. I mean, but in this main construction, you have just
it depends on the abelian groups.
Abelian groups, and
yeah.
that's how it works.
Okay, thank you.
All right, more questions, comments?
Question, Anna. So the concept of the multi-permutation levels and so forth was introduced to help understand the algebra that's going on behind the scenes here and enabled you to make these computations, if I understand this correctly. What I'm asking, right? But the question, is there physical significance to the involutive property? I mean, if you go back to the actual Yang, the actual equation solutions, is there some special physical significance to the involutive solutions?
This is a difficult question because, of course, I have no idea about, this physics and how it is. So I was always working with this set-theoretical setting as algebraists. And, but I think that, okay, good source because I don't want, to invent something, but this etching of paper, yes, etching of paper, I think will be the best source for, from this 1999, yes, which I mentioned here, will be the best source of, introduction to the topic and also explanation, yes, of the topic and why they started to work with it, yes.
Okay, good. Thank you. Thank you for a lovely talk. I'm pleased to see universal algebra swinging into action in new contexts like this.
Thank you.
All right, more questions? All right, if no questions, let's thank the speaker again. We were very glad to see Anna in our combinatoric seminar, and we will welcome you later when you come in April to visit in person. Thank you very much.
Thank you.